for Grade 12 Functions, or MHF4U, Section 1.1, Introduction to Functions. So in this tutorial, we're going to discuss a brief introduction to functions, the definition for representing the function, and multiple ways we can use to represent functions, graphically, algebraically, and numerically. So first of all, you may ask yourself, well, what is a function? A function is a way that you can represent real-life phenomenon using mathematical modeling. For example, on the graph on the left, you can see that this motion could represent a person throwing a ball to the dog, and so the graph is actually showing the motion the ball would take. And on the right, you can see the parent function for the quadratic function, which is y equals x squared. So you can see that with a couple transformations, the graph on the right can actually end up looking like the graph on the left. And so this is a concept that we'll explore in this course. So let's move on to the definition then. By definition, a function is a relation in which there's a unique output for each input. This means that each value of the independent variable, the domain, must correspond to one and only one value of the dependent variable, the range. So the independent variable is also known as x, and the dependent variable is also known as y. So basically what we're saying is that for every x you put in, there must be a unique y that corresponds to it. And also that functions can be represented graphically, numerically, or algebraically. So let's unpack this and let's look at examples for each part of this definition. When we say a unique output for each input, we can look at the example of y equals x, which is a simple linear function. So we can see here, once you put in x is equal to 1, you're going to get y is equal to 1. And when you put in x is equal to negative 1, you get y is equal to negative 1. And this is what the corresponding graph looks like on the right. So the graph of y equals x, you can see that every single point on that x has it has its own corresponding y. So furthermore, you can use function notation to represent functions. So what does that mean? So by function notation, what we use is f of x. And so f of x means that you're having a function of that point x. So the input is what is the x you're putting in, and f of x means the output, which is also known as y. So in this example here, we have f of x is equal to y, also known as 2. Next, we talk about domains. So domain and range, these are actually two concepts you can use to represent the x values and y values contained in the function. So when we say domain, we're talking about the x values that are included or allowed to be in this function. So in this case, in the example we have here, with x element of the real numbers, such that x can be between 0 and 4. So in this case, this is just an example that you can have of a function, and there are different number sets you can have. So that's what the first part of this explanation means for domain. So you can have the real number set, the integer set, things like that. And the second part talks about the values that x is allowed to be in the domain. So in this case, it can be greater than or equal to 0, and it has to be less than or equal to 4. And similarly, talk about range. So range is the same concept, but for y values in the function. So in this case, the example talks about y being element of the reals, such that, or real number set, such that y is greater than or equal to 0 and less than or equal to 5. So then we move on into the algebraic representation of functions. So I have two examples here, the first one being a linear function and the second one being a quadratic function. So in the linear function, y is equal to x, and that's to the power of 1, right? We don't always write the 1, but we know that x is to the power of 1, and that means that the function is degree 1. When we say a function is quadratic, y is equal to x squared, and as such we know it's degree 2. Okay, so now we can talk about representing functions numerically. So there are three main ways you can represent a function numerically. The first one is in a mapping diagram. So the mapping diagram, what it means is that the numbers on the left, these correspond to your x values, or your independent variable, and the numbers on your right correspond to your dependent variable, or your y value. So in this case, we say that -1 maps to -3, 1 maps to 0, 3 maps to 2, and 5 maps to 2. Furthermore, on the table of values here, we can see it's a very straightforward table. We have your x values on the left and the y values on the right. And finally, we have our ordered pairs on the right. So here we can see that the first value within this set will always be the x value, and the second value will be the y value. So the x in the first example, for example, you can see that x is equal to 1 and y is equal to 3. Okay, so the last representation we have here is the graphical representation of functions. So the most important thing to keep in mind here is that we can actually see the transformations that happen graphically when we see a new function, right? So for example, here, this is a transformed version of our parent quadratic function. So transformations are what are used to modify the function, and these modifications can be seen graphically once we graph the transformed function. So you may be wondering, well, okay, so now we know, what a function is, what different types of functions are, but how do we know if something isn't a function? So that you can use something called the vertical line test. And there's a perfect example here to show it, being the quadratic function and its inverse. So as you can see, this diagram might be a little bit confusing, but basically this right here is a quadratic function, right? And we can see that this is a function y because every single x value maps to its own y value. And so actually, if we took a vertical line and took it across the function, let's see if I can make that happen here. I'll use a clear line. Okay, perfect. So if we actually took this line and moved it across this function like that, if you can just imagine that line moving across the function, you'll see that that line only touches one point throughout the entire movement, right? But then as you see here, the inverse, circled in red, if we took that same imaginary vertical line and moved it across the function, it would touch more than one point, right? It would touch 2 points in this case. And that's how we know this isn't a function. So something important to remember here, though, is that when we calculate our inverse, as we see here, calculated the inverse, there's a restriction here. You can have positive or negative values taken, right? And so, in fact, that's exactly what happens here, is if you isolate, let's say, only the positive values of the function, then it is a function, right? Because, if you took the vertical line test through, you'd see that the line only touches 1 point throughout, and also because, and that actually means that each x value maps to only one y value. And similarly, if you isolated only the negative values of the function, the same thing would hold true. The only case here where it's not a function is when we have both the positive and the negative values of the function represented. And so that's it for the first video. I hope you enjoyed the video, and I'm excited to see you in the remaining videos in this series. And as always, thanks for watching, and if you have any questions, feel free to let us know. Thank you.